We're visiting here from New York, and I'm incredibly allergic to cats and falling apart here. So I don't normally sound this congested. Okay. So we have a couple of systems up here, and we made a point of not bringing out the new stuff until just a second ago, in case some people. This is actually the worldwide debut of these two new modules right here, right now. Real fast before I talk about those, I'm going to just give you a quick rundown of what it is that we do and what our story is. So because if I go away 1 foot. We're a New York City-based Eurorack synthesizer module manufacturer. We do all of our own manufacturing in our tiny, tiny workshop in New York. My story is that for the last years, I've been fixing synthesizers and building DIY stuff, and mostly a specialist on working on vintage Buchla systems. So when I decided to launch this operation, all of the designs are in some way inspired by the ideas that were in the vintage Buchla systems, but none of it is clones. It's all adaptations of these ideas and tried to be brought into what's happening now with synthesizers. Because of the advances in electronics in the last 40 years, it's possible to make analog circuits that are significantly smaller and more predictable than they were in the 60s. So we're able to do, you can't see them right now because the modules are all in boxes, but what we're able to do with these modules is make circuitry that in the olden days with the vintage and Buchlas and Moogs and that kind of stuff would have been stacks of circuit boards. We're able to do it on these in very thin modules that only go less than an inch back from the panel and have one circuit board. However, maybe just for fun, I'll take one of these out just to show. However, our modules are more dense than pretty much everybody else's. So what I would say is probably considered our flagship signature model is the Harmonic oscillator, which is a triangle core analog oscillator that is made from, the core is made from all discrete transistors, and then the triangle from the core is folded up in various ways to create to create triangles that are multiples, multiplied by 2, multiplied by 3, and multiplied by 4, etc., up to 8. And then those are all converted to sines. And then those signals are mixed together using this voltage-controlled mixer that has some tricks up its sleeve, allowing it to go across the various harmonics, sort of like a bandpass filter with a width and center frequency. With individual outputs for all of the harmonics and a mix out from that mixer. The other oscillator that we make is called the complex oscillator. It's down here. That one is more derived from the ideas that Buchla came up with when he was working on the 259, which has two claims to fame. The first is that although it has the basic wave shape outputs of triangle, square, and sine, it has a wave shaper section that addresses the sounds as from their harmonic content, not from their names, like scientific names, because of course saw, square, triangle isn't really information that relates to musicians. It's information that relates to scientists. So You have the ability with voltage control and with these knobs to mix if the harmonics in the signal are high or low, or if they're even or odd, or how much of those harmonics are in the signal. And then we also have a built-in, the second thing that Buchla did that was unique at the time, back in the 70s, was to add a dedicated harmonic, or a modulation oscillator to modulate the frequency or the amplitude and create more richness in patches. And that's part of what they call the West Coast philosophy, is the idea of creating patches that have harmonic richness created from simple sounds at the beginning, and the wave shaping and the modulation creating the changes in the sound, rather than the East Coast philosophy, which was to have rich waveforms from the beginning and filter them down to create the interest. We have what do we have? The dual 4-pole, which is a 4-pole high-pass filter and a 4-pole low-pass filter. We have which is discrete transistors, and based on the concepts in the Buchla 100 series filter. The amplitude and tone controller, which is a Vactrol or optical device-based low-pass filter with screaming resonance, followed by a totally discrete transistor-based VCA with separate addressing of the VCA, exponential and linear. We have the voltage multistage, which is a dual-channel 8-step sequencer that has switchable slides and gates and some tricks to make it usable in a lot of different ways, unlike anything else that's on the market. The multi-envelope, which is a dual 4-stage envelope that puts out multiple shapes at the same time. The only one of its kind in the world that does a delay, attack, decay, sustain, release, attack, hold, decay, sustain, release, delay, attack, hold, release, and attack, decay, sustain, release, attack, decay, attack, sustain, release, all at the same time from the same set of controls, with voltage control of everything and gate outs from everything, sweepable slope from linear ramps to full RC ramps. The scan and pan, which is a 4-channel mixer with voltage-controlled volume and pan on every channel, and the ability to sweep across the channels in the same way that the mixing in the harmonic oscillator works. A touch play keyboard, which is based on the ideas that Buchla did in the 70s. He created, I think, 7 different touch play keyboard designs, and although unique, this one brings kind of the greatest hits of some of the ideas that were in the various models to a keyboard that's based on gold-plated metal contacts that you touch, and how much of your finger is touching them determines what the CV out of the pressure output is, so that acts in a way like velocity does on a physical moving keyboard, and nothing moves. So that's also a West Coast specialty. And then we get to the new ones. So the 2 new modules that we're showing today and also at NAMM this week are the sequence selector, which is a 5-channel sequencer that is based on a core that has the ability to receive a pulse on every stage to jump to it, and send out a pulse on every stage, which allows it to step from any stage to any stage. And it also has buttons to do that jumping manually. And it has 1 row of sliders that send out a CV. It has a row of switches that send out gates. It has gates out on all the outputs, or on all the stages. And it has a 5-to-1 selector. So using this module, it's possible to use another sequencer like a voltage multistage plugged into the transpose input on the sequence selector and create some arpeggiator type sounds that play a short pattern that shifts around from these sliders, which I'll do in a second right now. If I can get sound out. I think I just do something that makes some sense. Over there. I'm getting that. So the transpose in is a unity gain DC coupled input. So whatever goes into the transpose in is mixed together with the CV from the CV row. So with this configuration, then the first stage of the voltage multistage steps forward the sequence selector, and we'll make it short. Also possible would be to use the multiple rows of the voltage multistage and select which one you're hearing. To make 16-step sequences, or rather than stepping the sequence selector forward from every first stage on that. It also has an analog address, so like a Buchla sequencer, you can select of the 5 stages using a voltage to select. So you have a 5-to-1 selector that's you can select by pulsing it forward like a sequencer, or by sending a pulse into the stage that you want to select at that moment, or from sending an analog CV. To select whatever stage. The second module that we're showing for the first time right now is called random sampling. So the random sampling takes some of the ideas that were in the source of uncertainty by Buchla back in the 70s, and it expands on those a little bit, and also includes a couple of other things that are unique to this. So starting from the top down, the fluctuating random voltages were done in all of the Buchla sources of uncertainty. Basically, it's a stream of random voltages going through a sample and hold, where it's clocked by a voltage-controlled clock, and it's filtered by a voltage-controlled filter, and they track together so that basically it's a random modulation source that's voltage controlled. With voltage control over how quick the modulation is. Now, ultimately, this will go into audio range. It doesn't right now because I was in a rush to get out the door. But when it goes into audio range, it will be able to be a noise sweep, which is similar to what you know from video games, like from the Texas Instruments chips, or when you played Atari games and they went. It'll be able to do that with audio in addition to doing these modulation sources. But an addition that I've created here is a random pulse, which is a bit like a Geiger counter, where you have voltage control over the rate of that modulation. So two of those. Then the third section is the stored randoms, which is in a way pulled from the Buchla 266, where you have a pulse input. Every time that's pulsed, it grabs a new random voltage, but it's actually a digital random selection. So it's not actually a sample and hold. It's drawing from a pretty limited set, and you have voltage control of what that limited set is. So you have, at one end of this control, you have one for the variable, which gives you 2 to the n, so 2 states of output randomly from one output, and n plus 1, or in that case, 2 states for that output, which so in that case, just 2 states, and if it's all the way up to 8 bits, then it's 64 states. A difference between this and the Buchla 266 is that the Buchla 266 uses a pseudo-random shift register, or a pseudo-random sequence generator that has a limited number of stages. So the sequence that's playing, you have control over how many bits it uses, but you don't have control over how long it is, and it always is only 64 steps long. So it actually repeats a pattern. So if you would play it along with you had it playing 16th notes with like a drum beat, you'd hear every 4 bars, you'd hear the same sequence of random voltages. But in this case, it doesn't actually do that. You're controlling how many different states you have, but you have a truly random selection of those states. Yes, Gary?
In source of uncertainty, Don uses a triangle wave as a source waveform, as opposed to, let's say, wobble bugs, which are sawtooth waves. What did you choose?
That's true, but actually in this section, that's true of the stored random in the 265, and it's true of the sample and holds that are in the fluctuating randoms. But in the so-called stored randoms, it's not actually a sample and hold. It's actually a sequence of digital values.
But I'm talking more specifically about your smoothed output. What are you sampling from? Is the core?
I'm actually not sampling from anything, because in my fluctuating randoms, my smooth outputs, the sequence, it's actually a pseudo-random sequence, a digital sequence, doing that as well, but also an infinitely long, a truly random sequence of a limited set of values. So
It's a digital.
It's done with there's no microprocessor, but as we get down, the noise source that's in this module is actually also a pseudo-random sequence generator, but it's 62,000 states long, and so 6 bits out of that are digitally sampled. So because that sequence is so long and it's so uncorrelated to the input that you're doing, it will be, for our purposes, truly random. And as a result, the distribution, the reason that Buchla would use a noisy triangle rather than just sampling the noise was because the distribution's different. So a noisy triangle actually has a uniform distribution across all the range of voltages. So there's no one area in the spectrum of voltage. It's from, in that case, 0 to 15 volts, but in this case that would be crazy because the power rail isn't even 15. So in this case, it goes to about 10 volts. And so by using a triangle, you'd get an absolutely equal distribution anywhere in that range is just as likely as anywhere else. So the way that those are distributed is the same as the triangle, not the same as noise. And actually, different colors of noise also have different like frequency or range distributions. So it's more like that, but it's done a different way. Okay, the next. Well, we'll talk about the noise then because I've already talked about it. So the noise generator here is actually digital, but what the synth DIY nerds will tell you is that actually digital pseudorandom sequence generators make more predictable and nicer noise than analog transistors or diodes do anyway, because when you make the noise from a transistor or a diode, you have to boost it by a huge amount, and in that process you boost all of the power supply noises and leakage and other things that aren't what you want to be boosting. So this digital situation is really great, and there were some chips back in the day, the MN5837, which was actually the noise chip, an 8-pin chip that was made for making noise, that was used in the Buka 266 and the Monopoly, I think the memory mode, and has kind of a bad reputation for sounding like shh, shh, shh. This doesn't do that because that was only an 18-stage shift register that, because of the length of the shift register and the speed that it's clocking, it's less than a second per cycle, which, although sounding like noise, has a periodic nature to it. This shift register is 24 stages long, so it's, and every time you add another bit, it doubles the length that it plays for. So this plays for a really long time before it repeats, so there's no perceivable repetition. There's some crackle in there, but it's not periodic. The pink, that's the white. The pink output is analog filtering on the white, and then there's a metallic output, which is 6 detuned oscillators that can be used to make. It's the way that the 808 and the 606 and some of these old drum machines made cymbal sounds. And if this is filtered in the right way, it can actually create a really nice create these kinds of sounds that we're sort of, and then like, you know, metallic cymbal type of sounds. The last section in this module is a 4-stage analog shift register. So Gary can probably tell you more about the history of the analog shift register than I can. But the story is that in 78, is that right? In 76, a Japanese gentleman who was working at CalArts he was the assistant to. Yeah, exactly. Well, more or less. He, who was working as an assistant in the music department, asked the guys who were running the department, specifically Barry Schrader, if there was anything that he would like to see in the Buchla 200 that wasn't there. And one of the things that they came up with was what they called an analog shift register, which hadn't been done at the time. So he made a series of modules that they added to the Buchla system that they called the Fortune modules, which, because his name was completely unpronounceable Japanese, everyone just called him Fortune. The analog shift register that he invented is a bank of sample and holds with delayed triggering mechanisms, so that you send a voltage into it, and every time that you send a trigger, the first sample and hold samples the outside world, and the second one samples where the first one used to be, and the third one samples where the second one used to be. And this turns out to be a really useful technique for doing certain kinds of, what do they call it, the classical music techniques where certain sequences of notes repeat on different voices. So I actually developed a sample or an analog shift register for a module that I made 7 or 8 years ago that I only made a handful of for Buchla users. And one of the things that I did in that process was that I made it 4 stages long. The next thing that I did in that process was made it actually hold, because famously the old sample and holds would droop really, really quickly. So once the voltage was sampled, you could actually listen to the pitch falling like half a semitone a second. And then when I set out to make this module, I actually thought that it would be sort of boring to dedicate that much circuitry to something that is a little bit specific. So I wanted to make those 4 sample and holds usable for other things and not just for this shift register. So this is a 4-stage analog shift register, but there are patch points that are normaled into the analog shift register, but they can be pulled out to use any of the 4 sample and holds separately. So that means that if you wanted to do the voltage echo thing that the sample or the analog shift register does, but you only need to have 1 echo, you can use 2 of these sample and holds for something else and just use the first 2 as the analog shift register. If you are doing some crazy patch that involves 4 sample and holds for whatever reason, I don't know, you can use them all separately. But an interesting thing about it is that in order to make the analog shift register work, the trigger in that makes the process go forward actually has to have a short, less than a millisecond delay, so that the 4 sample and holds are actually flammed with their triggers. And so that means that if, in this case, if the inputs are given, and I don't have the mults handy to run the same thing to all 4 of them, but if you would plug noise in, well, in this case, if it's plugged into the well, it's kind of hard to tell by looking at it because the voltages are small. But if you send in some signals into all those sample and holds, like if you sent the same noise or the same triangle or whatever into all of those inputs and then hit the trigger, the flammed sampling actually means that you would get 4 uncorrelated random outputs. So it actually can function as the stored randoms on the Buchla, but it can act as 4 of them at the same time from the same source. Or 3 of them in a sample and hold for something else, or whatever. So this is a section that I'm probably cursing myself again to something that most people won't understand what I was thinking. It can do some interesting things, but it takes a little bit of imagination to come up with a use for. So initially my thought was that this could replace the stored random idea entirely. Yeah, I'm told that I have to wrap it up. This module was completed the night before I came here. And it's a prototype that if you saw the back, you would understand it's nowhere near shipping. Yeah, I don't know. I can't even tell you.
I think we'll ship like within a month.
Yeah, well, again, we do. Yeah, well, we've manufactured. To give you an idea of what our production scheme is like, the front panels are manufactured, but the circuit doesn't work yet. Because we do our own manufacturing, the turnaround is faster than it could be. So we should probably be ready to ship in about a month, maybe 6 weeks. And in that process, we will determine what the price is.
All right, so I'm gonna throw a bunch of stuff at you guys.
Okay.
Our logo patch cables. Here's a